Welcome, this is a C++ 20 Firehose talk. I will just give you features with a few examples. I will not be teaching you all the features in detail, that would be impossible. I hope you get a nice overview of what features we do have. There's going to be a bit of overlap with Timo's talk yesterday. I'm sorry for that. The features are the same. I focus a bit more on the library. I also have some of the big features in there. So I'm Fabio Fracassi. I am the German national representative in the C++ Standards Committee. That's a grand-sounding title, but it just means that I show up regularly. I also work at a university here in Berlin. We do applied science. We do very practical education. And let's get started. So the first feature, which is really a great feature, is format. And format gives us all those nice formatting things that you might know from Python. You can do very fancy things, like you can create a width from a formatter, like from a parameter, and like have different styles. So you get this one out. So what we have in the standard is just the format that formats into a string or any other buffer. You have to do the output yourself via something else, puts or cout. One thing that's very nice is that we will be able to get good Unicode output formatting if your system supports it. That is not standardized yet, but we allow it. We don't do anything that hinders it. Nice thing about it is very performant. It's faster than printf. So finally, you have no reason to use printf anymore. It's also very conscious of binary bloat. It helps, so it's not a template explosion. It will be very, very efficient and do not cause binary bloat over your, even if you do much formatting. And you can extend the format syntax. You can do your own adaptations for your own types where you can give parameters in the format string. Okay. So I was speaking about Unicode, and one thing we did to help it is char-it. Char-it is just another fundamental type which can handle UTF, or is supposed to handle UTF-8 data. And what does it do? It never aliases with any other type. So if you do types of a string with it, you will not have the performance penalty you have with normal strings, that it has to do alias analysis. So the optimizer can be better. It's always unsigned. That's a nice thing too. It's easier to do portable analysis of the chars in there. And then that's the most important thing. It can be overloaded upon. It's not a type def. You can have several functions, and it will always select the right one. So this is a breaking change. If you did this in C++ 17, this is a new feature from C++ 17, which worked like that, this will now break. Sorry for that. But we really wanted to have first-class Unicode support at some point. And the way to get there is this. We have to have this overloading. We have to be sure that if you have UTF-8 input, you will get to functions that can handle this, and that other functions are not called. Otherwise, we won't have a compatibility story. That's what we did. So this breakage was uneventable, so we did it. You've heard this in the keynote. This is Howard's chrono library. It's the extensions for the chrono library with calendars. You have seen the keynote. It's an amazing feature. It's an amazing feat of engineering. I really like the type safety of it. And if you have ever worked with time zones and did the calculations in there, this is so much better. Yeah. I don't want to say much about it. You have all heard it. Another small feature which is really great because it helps us to prevent using macros, is source location. And source location is a curious little library feature that has a very little piece of magic in there. So what it does, the magic is all in this one constructor or in this one factory function in the current. So what it does is it gives you the current source location, like line number, file name, function name, I think sometimes even columns. And it does this with a nice little trick, and that is the default parameter. What you put in there gets evaluated in the context of the caller. So that enables us to with a little intrinsic in here, you can always get the source location of your caller. And what you can do, so you can write a logger, and this will output the file name and the line number without using any macros at all. That's amazing. Okay, one of the big ones. Concepts. What do? They constrain template parameters. Up until now, when you had a template parameter, you could put any type in there, and then sometimes down the line, if you did something that the type doesn't support, you get this huge error messages. Now you can say, first you can say, this is my concept, this is something a type has to support. It requires a type or two instances of a type, and those should be comparable via the equals. And the result should be bool. This is a concept, and you can use it in the template. You say, I want this type to be equality comparable, and I want this type to be a range. So this is nice. This will give us better error messages. You do something nonsensical, it tells you this is not possible, find with widget won't work because it's the wrong one, because it's not a range. Of course, you can even do more complicated concepts here. You can have better constraints. The one I showed you before was over-constrained. Here we are a bit more precise. We want that this type is comparable to the type that's in the range. That's a bit better. It allows for a bit more flexibility. What concepts don't do is function definition checking. So function definition checking would mean that it tells you if you use something inside of your template, of your template function, that is not covered by the constraints you have. And if you do something like this here, you have a log function somewhere inside, you don't have any requirement that says that this v here, that this value is somehow formatable or streamable or whatever. Yeah? You didn't write this here, so it shouldn't work, right? Well, by design, we did not do this because it would make it very hard to use this feature. Whenever you would have logging, you would have to write a concept for that. You would have to cover all your bases there. So now it just works like a normal template in this regard, so you will get an error message much later if you do something which is not formatable. That's what it is. Okay. One thing that fell out of concepts is generic functions. You knew that you could do something like this with lambdas, with generic lambdas in C++14. You can now do this with normal functions, and this code here is exactly the same as if you would do this. This makes template code quite a bit nicer. And you can do this also with concepts. You don't. Auto is basically the unconstrained concept. So what you can do, everywhere you could write auto before, just auto, you can write concept auto. And this allows you to have a template that is constrained. So here, the C will always be a range. And you can also use it for local variables. You can do something like, this is edible, so I want whatever falls out here, I want it to be edible. And the compiler will tell you if it isn't. Okay, concepts is a nice feature, and it allows us to do ranges. Ranges will take some getting used to. The alternative code, if I would write this with normal raw loops, would probably be more familiar to most of you. But having worked in a code base where this is used throughoutly, once you get used to it, it's just so much better. It will prevent so many problems you have with raw loops. It's a different game. We often forget that we learned raw loops very early, like in the very beginning, and we often forget how hard they are. Lots of bugs hide there. So, what do we have in ranges? We have the most important views, filter view and transform view. We have an iota view that just gives you lots and lots of numbers. And we have join and split view and a few others. Join and split view, you can join two ranges one after the other, or split after with some criterion. You can split a range to make sub-ranges out of it. So ranges are not quite what they were before. Ranges before were always two iterators, like two positions, and at some point you looked like, am I at this position? Yes, then stop. Now they can also be an iterator-sentinel pair. And with that, you can model things like an old C string with a zero-terminated string. So you can say a sentinel is the reference iterator that I'm getting, that I'm comparing with. Is this 0? If yes, then that range is at end. And that allows us for very efficient ranges for C strings, for example, but also for unbounded ranges. And this is, for example, this iota view. Iota starts with the number you give it and then produces integers forever. Well, until they overflow, but forever. And then you can do things with it. And the nice thing about ranges is that they are lazy. This one will not generate an infinite range of integers, then transform them all to their squares, and then take the first 5 and throw the rest away. That would kind of be inefficient. No, it just takes the first 5. It lazily goes there and just does the computations you need. If you have been to the quiz, you will probably have seen that. So, what comes with the ranges library? We have the basic concepts. We have copyable, we have regular, we have a concept for range. We have some range access traits, something like iterator type, value type of a range, so that you can easily ask questions about the range and do this constraints. Is this value I'm getting here in the find, is this the same as the value type of the range, so that you can do stuff with it. And this is probably the one you will be using most in the beginning, the rangified STL algorithms. All the nice algorithms you know and love with ranges, and what this allows to finally do that, what we always wanted, just sort a vector, all of it, no begin, no end. This now works with all of the algorithms. Okay. So there's a few ranges features that are missing and will have to wait until 23. We just ran out of time to get them in because they are a bit more complex. And that's zipView enumerated and ranges 2. zipView takes two ranges, puts them into one range of pairs, of something pair-like, and then iterates over that. So with that, you can do something like a vector and the numbers of the vector, and then like get every second element. And then the ranges 2 allows us to take this range, which is this lazy thing, and concretely put it into vector again. This is quite a nice syntax sugar thing. Enumerate, you might know from other languages like Python. It takes a range, like a vector, and gives you a pair of the element number and the value in the range. This is useful a lot of times, and those two would allow us to get rid of the last reasons to ever use a for loop with a normal initializer, like not a range-based for, well, soon. Sorry. So there's also a few small improvements in the algorithms. So for example, list remove, all forward list and list, they have the remove and the unique algorithms, they return the number of elements they removed. It's just information the algorithm has anyway, so we can as well pass it along. This one is very nice. If you ever fell into the trap of doing remove and expecting it that it removed the elements, actually doesn't. Erase is what you want. And like normally this is quite a mouthful to say. Now you can say it very easily. And then we have a new execution policy for the parallelized algorithms library. It can use unsequence, and that's for vectorization. If you have some loop that allows for vectorization, this is a policy you want to take. Okay. Closely related to ranges is a span. A span is a vocabulary type for consecutive ranges, contiguous ranges, and you can use it like string view. You can use it to abstract away the container, the ownership of the data, and just get the data. It acts like a reference in this way, so it can be dangling. Be careful with it, like with string view. But it's very good as a parameter to abstract away all those things. We have two variants of it. One is bound, like compile time bound, and that's very good if you want to like have vectorization or something like that. It can help there if you have mathematical operations. It can also be a good thing if you do some parsing and you know that the token you're looking for has an exact size. And what this does is it checks it at compile time. So it's statically checked that the array really has 3 elements. And it will not compile if it has too little elements. And if you do it with a dynamic size, if you have it with a dynamic size, this will work. And then you have a runtime check. You won't have a runtime check. Then you have the normal thing. You have to take care that it will not, that you don't pass in too little data. Okay, so this is dynamic. Span is a bit curious as far as types goes, but that comes with it being a reference kind of type. It's not a regular type. If you assign a span to another span, you get a shallow copy. Comparison, however, is deep, so it really looks at the elements in there like string view does. Which is strange because span is allowed to modify the elements. It's not always const like string view, but it's useful in that way. And there's an easy way to get subspans, and this thing helps a lot with parsing things or something like that. It's also useful as a bridge to low-level code, but because we often have buffers, and because it's writable, you can use it in that way. And there's this helper functions as bytes and as writable bytes. And what this does is basically a reinterpret cast. And for that reason, it was also heavily contended. Some people said this is a much too nice spelling for something as dangerous as a reinterpret cast. But I like it because that way, reinterpret cast gets even more dangerous, because that's one of the cases where you really want a reinterpret cast and have to use it if you interface with C libraries or something like that. You can now use this one, and whenever you see a remaining reinterpret cast now, you will be even more cautious of and more skeptic about it. So, speaking of which, I have this function, make unique default init. Now I do an assert. This is 0. So who of you thinks that this is okay? All the elements will be initialized with 0. Oh, okay. Who thinks that might fail because there are unknown values in there? 1, 2, 3, 4. Okay. How many think it's undefined behavior? Okay, a few. Well, it is undefined behavior. You cannot read from this. This is really uninitialized. And we want to name it this. Right now it's called default init. We want to call it something that makes it clear that it is undefined behavior. Uninitialized, indeterminate, we don't care, just not default init. We hope we will still get it in. This one will be talked about in Prague. We will see. So, speaking about low-level stuff. We have a bit of bit fiddling. Bitcast is new, and you can use it to really cast the bits of one type to another. Some people did this with reinterpret cast. That was always wrong. That was undefined behavior. You could have used memcopy for this, and this one makes it much nicer and helps the optimizer to do the right thing there. Then this is another little feature that Howard Hinnett did, and it detects the endiness. And if you look into how it's defined, it's so brilliantly simple. It's just an enum. It's just an enum. It's really great. Look it up. It was one of the shortest proposals we ever had. It took like very little time. This is great. And we have a few bit operations also that work on just bit fiddling operations, rotate left, pop count, things like that. Those are very, very thin wrappers basically over assembly instructions that you sometimes need for very efficient code for cryptography or things like that. Okay. It's time. Okay. We should use lambdas a lot, right? We like using lambdas. We use them with our algorithms. We can do funny things with functional style programming. So we fixed a few bugs in those. One thing which we couldn't do before is saying something like this. We want a vector. We know that we want a vector. We don't know which type of a vector we want. So this wasn't expressible in lambdas before. Now we can. We can now add pack expansions to the capture of a lambda, which is also very useful. You can do stuff with like binders or something like that more easily with less boilerplate. That is useful. We also have a new library function, bind front. You might have heard talks about why bind is deprecated, that bind is deprecated. And all the reasons for that are true, but there's one use case, and that's the one where you want to bind the first few parameters of a function. For example, if you have an object, you want to bind the object to the call. This is a very common pattern. It's often called delegate or something like that. That's very useful. And for that, lambdas are clumsy because you have to repeat all the parameters. You have to forward all the parameters. And you just don't want to do this. Bind front is much more lightweight than std bind. It can do just this use case. It cannot do parameter reordering or stuff like that. It can do just bind front. And so with that, you can create delegates, you can do kind of currying, and that's very useful. Okay, the next big feature. So we have modules. Modules have a name. You say, I have my module. I say I want to export this, so this is a interface module. Then you can import other modules. they are not by default re-exported unless you say so. You have stuff in there that's private to your module, that's not re-exported, that you can use as internal details. And then you have stuff that gets exported. So everything in this namespace will be exported. One thing that's important to notice is that modules, the module name and the namespace name, they don't have to be the same. They have no, there's no connection in there. The module name is purely for linking. The namespace name is purely for the API side. And then you can use the module by importing it, and that is it. Looks easy, right? Why did it take so long? Like, that's really easy, right? So it's not. It really changes fundamentally the physical model of how we translate C++. It changes how linkers have to interact. And mostly it manages to work with just our linkers. But really how things work, like the ODR violations, things like that, that really changes. It causes changes in, or requires changes in the build systems. You have to be aware of what you're building there. And finally, it will change how we think about modularizing code. So the effects of this will be huge, and it will take a while to get used to. Modules have been highly anticipated, and many people have many ideas what they are and what they should be. They are not a magical bullet. So one thing they will not do is magically make your code modular. If you have your big ball of mud code and slap module on it, it will still be a big ball of mud. If you have a nicely modularized libraries, modules will help you to get even better, like physically improve the details of that. But you still have to do the modularization yourself. It will not magically make a package manager appear. They don't really help with distribution. They won't make interface and implementation files obsolete. You might get away with more in that regard, but it will not fully make this obsolete. And it will not magically improve build times. Well, there's hope. If you've been to Daniela's talk, this looks promising. So they might get quite a bit faster build times, might give us quite a bit faster build times, but you probably have to work for it. So we have coroutines, next big feature. So one way to use coroutines is as a generator. And that's kind of similar to the unbounded ranges we have seen. And it also integrates nicely with that one. So what you do, so we have a coroutine here, and then we use it. So how does it work? So we call it and start the coroutine. Then the generator here produces an infinite range. Well, it doesn't have to be infinite, but right now it is. It doesn't have to have an end predetermined. It can run, and at some point the end will come. And this is the first keyword, co-yield. When you co-yield, you will produce the first value, give back the execution flow to the caller. Then the caller will run, output that value, go back. We jump back into the yield part, produce the next value, yield again a lot of times. At some point, and that's important, not the coroutine itself says, I'm done, but the user says, you're done. I'm done with getting values from you. You might have realized that I've slapped this non-standard before here, and that's because this generator thing is not in the standard library. there's a library of Louis Baker, CPP Coro. This repository is also a very good resource for getting to know how the details of coroutines work, what you need to implement to make them tick. And he has some very good tutorials. In my opinion, the best tutorials on coroutines that exist right now. Similar, and that's probably the more anticipated use case for coroutines, you can use them for asynchronicity. There you need something that's called a task, which is a future-like thing. And with that, you can create asynchronous routines. And they work like this. You have, this is an echo server. It reads data from a socket, and then it waits. So it gives back the control to the caller of this coroutine, so you can do other stuff while this thing here is blocking and waiting for the read to finish. And once it's finished, execution commences here. We do the next thing. We write it back to the buffer, co-await again. Other people can do other stuff while this is waiting. And then once it's done, we go on here and start it again. So that way we can write asynchronous code in a very nice, concise way. We don't have to handle callbacks all the time, go back and forth with it. We have a very good way to write this now. So coroutines are the language feature. We do not yet have much in a way of library. Those features will probably be those things we will be working on most for the C++23 timeframe. We will try to get in all those building blocks that you need to run the coroutines on a higher level. Right now, you have to implement all of those things yourself. And one thing that's important in this area are the executors. That's a big thing that will help with all kinds of asynchronous operations. It will help with audio, everything that requires an event loop, basically, and requires you to handle and control where something is executed. Okay, speaking about asynchronicity, we have a few features that are new in threads and synchronization. So one thing is JThread, and JThread is a joining thread. What it does is that it automatically joins the thread in its destructor. You might know that with a std thread, you have to make sure that you either join or detach at the end. And that's kind of irksome, especially if you want to handle errors. So if you have an exception somewhere thrown in the work you do here, you better make sure that it's joined in any case. Otherwise, your program will crash. So standing just like that, this is nice. This makes code a bit easier to write. But it just replaces a crash with a blocking. Fair enough. But what makes it really useful is that it allows us to do cancellation of the threads. And this is a stop token which comes together with the JThread. And the stop token allows us to do cancellation. You can do it in this simple way. You wait for the stop token until a stop is requested. And this is fully thread safe, of course. But what's more important is that we have adapted logs, mutexes, condition variables to also take stop tokens. And that way you can wait on something. You do a log, you block on this log, or you block on a condition variable. And once a stop token, a stop is requested, all of those will break out of it and go out of your code and resume, make you able to cancel. It's still cooperative canceling. Like the thread will not be killed for you. If you hang anywhere else in your thread and don't give back control, you will still have a blocking system. But you're now able to write a good shutdown of all your threads. And this feature, this is really not easy. Like there are lots and lots of cases and lots of opportunities where this stop token handling can raise. If you look at the implementation, it's quite involved. So you don't want to do this yourself. So this is really, really helpful. Okay, we have new synchronizations. And I'm not smart enough to explain those to you. So I'm just going to throw this here. We have latches, barriers, and semaphores. We have atomic weight. And if you've been to Bryce's talk, or if you're watching this online, go to Bryce's talk about the new synchronization facilities, because he will explain it, and he won't tell you something which is just wrong, which would happen if I would do examples here. So we do have some nice things in atomics. Float, double, and long double now work. You can do those in an atomic fashion. That's very useful for many kinds of work. We do have atomic shared pointers. This allows us to overwrite the shared pointer itself, not just like shared pointers were thread safe before in an atomic non-blocking fashion, but just the control block. Now it's also the value that's inside the shared pointer. This is what allows you to do this. We have an atomic ref. So sometimes you have types or you have values from a library that you can't modify, or an interface you don't want to modify. And in this case, you can't create atomic versions of it. Now you have the possibility to create an atomic ref to a normal variable. And then if you access the variable through this reference, then all the accesses will be atomic, like all those that go through this reference. Okay. Next big topic. We want to use const_expr at a lot of places. Maybe not all the things, but at a lot of places. So we extended the story there a bit. We fixed some holes in this story about const expressions. So we do have const eval. Const eval is a tag you put on a function to enforce that it's never called at runtime. So you have this function, it's annotated with const eval, and this works. You use it in a const_expr context. This is okay. If you use it in a runtime context, this is not okay. This will be a compile time error. Okay? This is useful. On the other side, we have const init. Const init applies to the variables, not to the function. It's a modifier of the variables. And it applies to global or thread local variables. And what it does, it makes sure that the initializer is done at compile time. So you have a function that's always runtime, and you have a function that is const_expr, but can be constant time, const_expr time, or it could be runtime. So it could be compile time or runtime. So if it is, in fact, compile time, this will work. If it is, in fact, runtime, it will not compile. So it will make sure that it's always initialized before the program is run. And this and a few other core features allows us to do the great const_exprification. So we have added const_expr to a lot of library features. And not only the ones you would expect, like string view is pretty obvious that you can do that. You could probably, if you wrote your own string view, you might have done this already, or std array, things like that. But we can also do it with string and vector now. And that's quite impressive. Of course, we also added it to all of the algorithms, or a lot of the algorithms, so that they can be used in const.expr. And why do we do this? We want to make the compile time programming as similar to normal programming, to the normal runtime programming as possible. Because both is just programming. Why should you use a complicated template metaprogramming thing where you use types for values? We have a good language in C++. Why shouldn't you use real C++ for that? And what it allows us to do with another feature we need is class types and non-template parameters. So with a const.expr string, we can now put a pattern, for example, in a template parameter. And if you have seen Hannah's amazing talk, you will know what will come. So this allows us to do, for example, regex parsing at compile time with a very nice syntax. Of course, C++ initialization is complicated, and of course we added new features to initialization. Hopefully this makes it easier. So one thing, we adapted designated initializers from C. It's one reason for that is compatibility. And the other reason is sometimes it really helps readability to be able to have the names. We did not do all of the things that C is able to do. We cannot do out of order. We cannot do nested initializers. And we cannot do mixed initialization. Mostly because in C++, order is important. So there are, lifetime is important, order is important, so we cannot just do this. So we add on the side, like, let's be careful, we can always add more features later, but this thing will work, and it will give us a few nice things. So this one will hopefully make it, make initialization a bit more uniform. So we can now initialize aggregates with the parentheses, with the syntax of parentheses. And this is very similar to what the brace initialization does. It will not call the initializer list, and it allows narrowing conversions. So if you had a point with two integers, that's an aggregate. With normal aggregate initialization, this one would fail because it's a narrowing conversion. This one will work. And on a similar vein, we have more deduction guides, template deduction guides. And if you have a templated point, you can now do the initialization, and it will deduce that this is a point of doubles, and this is a point of ints. And it also works for alias templates like PMR vector, which is an alias which didn't work before. Now it can correctly deduce that the type that you want to fill in here is an int. So you can use it in a lot of more places, which makes it more uniform and more predictable. Doing for time? Oh, that's okay. We have a few new attributes. So one is likely, unlikely. Just an optimizer hint. One thing you might want to use it for is something like this. You might have something that might fail with an error code, and you want to say that it's unlikely, so that the performance is optimized for the good case. Yeah? No discard can now have a reason. Like we slapped no discard also on very many of the empty things because that finds real bugs. Empty, if you don't know, is empty, not clear, what many people think. So now you can also put it in your error messages why you shouldn't use a function and what you should do instead. So this is quite nice. No unique address helps us to conserve memory in your structs. Right now, you could do this, but you had to do this empty base class optimization. You had to write your code in terms of structs that depended on the other structs and did inheritance. Now you can just slap this attribute out of it. And if this is an empty class, this will not take memory and cause padding issues. This will just go away. So that's most of the features. Thank you for your attention. So feel free to ask me at the break. We actually do have a bit of time. I didn't expect that. So you can ask a few questions. There are a few features I didn't talk about. Most notably, probably the spaceship, because this had a few last-minute changes, and I didn't feel prepared to come up with the exact right thing we nailed down at the end, because I was not there to visit it all. So this will take a bit of time until good tutorials come out that use the last syntax we decided upon. There are a few things like mathematical constants. We have now a std number pi and a few related things. We have quite a few new traits. We have isconst and evaluated. We do have this funny thing, include version, which just gives you the C++ version, which causes some trouble if you have your main thing in an include path and have a file that's called version in it, which some old, outdated build systems do. So lots of features. Questions?
Hi, thank you for the talk. I was just wondering, given that most of the ST algorithms are const expert now, does this mean that they internally condition on like if they're in a compile time context? I'm thinking about like std copy. It can use memmove right now, but like if it's const expert, then does it have to like check?
Yeah, they might do that. Like if they do this optimization, they will probably do that.
Okay.
Oh.
All right.
More questions?
Okay. Thank you.